Hey everybody, welcome to our inaugural episode of Super Simple. I'm Marc Teer, the founder of Black Spectacles, and I'm thrilled to kick off this new podcast. It's actually, it's like 5 or maybe even 6 years in the making, so it's really exciting to finally get to this point. The idea behind Super Simple is to really kind of get into the how in architecture. So we're going to focus through this podcast, we're going to focus not so much on the pretty pictures, but instead how designers are using design technology to realize their world-class projects. So we're going to try to talk more strategies, than where the move button is in some software or something. So that's kind of the big idea behind Super Simple. And I have to say we're really lucky to be able to kick off this podcast with John Shields from Point B Design. John has a firm that is based in Philadelphia. And he has won an AIA Technology and Architectural Practice Innovation Award in 2015 for his D-Bridge project, and that's what we're going to talk about today. You should know that John's practice is unique in that they work to focus both sort of on high-tech and low-tech tools to solve design problems, which is going to be evidenced in the project we talk about today because he has some really interesting strategies around how they iterated between the digital world and the one-to-one scale mock-ups that I think you guys are going to find really impressive. So that's what's on tap for today. Before we get started, if you'd like to register for our next episode, our second episode of Super Simple, it's going to be on June 8th, and it will feature Andrew Watkins of Ayr St. Grove. He's going to talk about how they used digital coordination to realize a ton of value during the design and construction processes on their AIA TAP Award winning project, another winner from last year, for the University of Delaware's Interdisciplinary Science and Engineering Lab project. So you can register for that episode at http://bksp.es/supersimple002. We'll share that link with you later as well. Today, just as a side note, you guys know that we have design software tutorials taught by world-class architects like John on blackspectacles.com. So make sure you stick around until the end of this episode because we have a special Black Spectacles promo code to share. So stay tuned to hear about that at the end. And tonight we'll be taking questions using the GoToWebinar question box for those of you who are attending live. As well as on Twitter using the hashtag SuperSimplePodcast. So to get started, again, I want to thank you, John, for sharing your work with us today. And I wanted to start off maybe by asking you, can you tell us a little bit about the D-Bridge project in general first?
Sure. You want to go to the first slide then?
Yeah.
So this is an exterior view of the project that we're discussing today. The project is a connector between an existing residential structure outside of Philadelphia, Pennsylvania, and an art gallery, which my firm designed in 2010. So we had a previous relationship with the client, and when we originally did the gallery, we opted not to connect the two buildings because there was so much emphasis in the early design concepts on the way in which the garden related to the artwork in the gallery and how much change we want to evidence in the building and in the reflections of the building from the landscape. So we wanted this diaphanous, connector, and so the bridge, as once the client started using the project, he wanted the weather connect because the project was proving to be quite successful for him. He was really happy about it, and he just wanted more gallery space as well. So we were going to use this space as some sculpture as well as some glass that he collects. So next slide. Okay, so we this is just to make sure I acknowledge that we work collaboratively. We both as a team internally and externally, we're very open source with our information. We're a very flat structured firm. As Mark said, we're high tech, low tech. So we have a 4,000 square foot wood and metal shop that's always been a part of our practice, and we use that to test new materials and to test systems that we are trying to incorporate in our design projects. And we use digital design tools that we build ourselves, often in Rhino, Grasshopper, and some of the plugins in there. We use Maya up front. And So hopefully this project will evidence some of that. So some of the people that we specifically collaborated with on this project, Keyston Hood is our local structural engineer in Philadelphia, and we've done a lot of projects with them, and also the gallery project that this building connects to. We work with Front Inc. from New York City, Mark Simmons' firm, and those guys we did the entire building gallery project with in 2010. And so when we started with this project and we started to get more involved with the feedback loop of structural analysis as part of our earliest design inquiry, Mark gave us 2 assets as a full-time, unspecified, let's figure this out when we know what we're up against kind of relationship. And as it went on, Vish and Keon stayed on the team straight through to the end. So next we have, you can go to the next slide. This is an interior view of the bridge from a rendering. Our team members at Point B that worked on the project were Sam Rosen, Priya Mehta, Tom Ecchiavetti, Josh Jordan, Jim McKenna, and myself. Next slide. The project was fully developed between April of 2014 and September of 2014. We really had done some conversations back and forth with the client, but until April of that year, we hadn't really hit, the foot on the gas, so to speak. So all of the work that you'll see tonight and a whole bunch of other images of the structural analysis side, I took out. I wanted to keep the conversation today focused on the way in which we use our custom-built design tools and the studio to make design decisions, what we call probabilistic solution sets, in which there isn't one specific, but there's rather an emergent bottom-up set of designs that move forward. And so hopefully this will evidence that. So next slide. So this is taking the bridge and pulling it apart. Here you see the exterior layer of tiles. These I'll come back to later. I just want you to have in your mind as we go forward some of the parlance or the nomenclature. So there's a waterproofing insulation layer, and what we're calling voxels are visual or three-dimensional pixels, basically. And visual voxels are a skin surface that reports onto the structural voxel layer, and snoots and glazing refers to the glazing system and these concrete portal frames that were part of our strategy to decouple the buildings from the bridge. So, okay, and the slab. Okay.
Now, John, if I can ask, so just going back, the project that that you're showing here, the D Bridge project, it's maybe just to give us a sense of kind of where the project is in I guess what status it's in. It's, I think, can you tell us sort of where this project is in terms of its completion?
Yeah, so up in September, we had completed all of our, you'll see the later slides, the versioning of the voxels and the structural analysis. We were completely ready to go ahead and fabricate, and the slab is in currently. The foundations are in for the feet of the shell structure, and the snoots have not been cast yet. The client put it on hold due to some other issues that he had. He had a couple of other architectural projects that were ongoing simultaneously, and it was becoming too much at once to focus on it. So we're currently in a holding pattern right now.
Okay, so partially built, awaiting the good stuff, I guess.
Yeah, but fully at the launch point, frankly. All the information, engineering, commissioning of all the glazing package has been figured out. So. Okay,
cool.
The next one, this slide shows just the property and the context for the bridge. The red rain screen structure is part of the gallery, and you see the undulating roof out there. The glass out there is 20 feet tall, 9-foot wide panels, triple glazed with every intersection is compound angle, and was quite a project to build. So this.
And John, the bridge that you sort of see here, this is the location of the actual.
Yep. So we built an epay deck that connected the two, and the profile of the ultimate slab that we cast isn't exactly like that, but we had certain things packed into that deck that we preserved. So. And there's a shift in topography that you see just past your red mark. There's a drop in of 23 inches or so off of the deck down to grade. So there's a little pitch to the side. It's relatively flat between. This meadow that we're looking at in between here with the sycamore trees, that meadow, because of the way that we developed the gallery, that meadow is planted with, we call it a synaptic garden, between these two building faces, and it fires with various, blooms, and in some of the pictures you can see the grass is up to almost 3 feet high. The meadow changes dramatically during the year as part of the design parameters here.
Okay.
So early in the process, we were knowing we're going to connect, but not knowing what structural system. So we're fishing around for formal studies as well as, structural logics. We had called up Keystone Hood and asked those guys about investigating a set of acrylic frames. We were thinking of carving some, as you see in the lower right image, some, skeletal like portal frames made out of acrylic at like a 3-foot interval or 4-foot interval. And then we looked at doing a composite structure with carbon fiber or fiberglass shell structure, and we looked at doing a grid shell as well. And then we kind of moved through those. We ended up with the concept of trying to do a thinner self-supporting shell structure. You see the blue image in the middle. The concept of making it up of discrete parts was preferred because, you can go to the next slide and I can talk through the flow here. This is a little diagram of our flow. So on the left is, what I would call problem setting, and in that phase we were discussing ways in which to keep it less invasive on the property itself. The garden, after our 2010 construction, had gotten to a point where it was really firing well, and client was super happy with the way things were on site, and the art collection was rolling, and we just didn't want to come in and set up a huge construction zone and stick build something on the property. So the concept was to have things made in discrete parts that could also flatten out the fabrication timeline. So we were thinking of it right from the beginning as maybe doing this kind of voxel structure. So you can go to the next. Here, this is just a zoom in of the left side of that diagram, and talks about what we were looking at. One of the caveats I said to Mark earlier is that this is a very nonlinear, multi-scalar process. We're working at full scale day one. We're building stuff at full scale to test some of our concepts, and we're working at very fine grain and trying to figure out this structural system, and many different softwares, many different people looking at the softwares, and we're trying to build up a bolus of information at this point in time that something's going to start to have a little bit of inertia. If you would picture it like a swarm of like bees or something, that this kind of builds up and it gets its weightedness to the early investigation. So that's why I call it problem setting, because we're producing a lot of models. We made hundreds. You'll go to the next slide.
Actually, if I can pause here for a moment, it's probably a decent time. I know you've talked about using mind mapping software, to kind of shape, I guess, your process, your design process, or as a tool for helping you visualize your process. Since we're looking at these diagrams right here, can you just talk a little bit about how you're using mind mapping software in your practice?
Yeah, because our stuff is nonlinear, and we are also we have a very specific, defined set of concepts up front. We'll talk through it. We'll talk with our clients. We develop something that's what we call our lofty goals, right? But between the lofty goals and moving through a day in the studio with a bunch of guys who are young, relatively young, and many different levels of experience, you need something to give them liberty to run at different paces and run at different depths of consideration, different angles of attack, and yet still have that concrete, we know where we're going. So oftentimes I'll bang out a mind jet or mind map tool early and use that as, kind of just a brain dump, but then it gets hierarchically organized, and also we can use that as a relationship for time forward scheduling. The other thing that we do is we use an Excel spreadsheet that we built, which uses it's a timesheet that we use, which is based on percentage only and not on, everybody takes the number of hours they want to work, but we'll parse components of the project up into, weighted percentages, and then we distribute the load into people's work week by saying, this has X percent of your time. I don't know if you're going to work 3 hours, I don't know if you're going to work 75, but of that, this hierarchically has that. So between the mind maps and that timesheet, it helps allow what we think is the psychology of the person on the team that is working on the piece has to be in the optimal state. You might want to feel like working on something one day, maybe working out in the shop because you had a rough day the day before, or you want to just put headphones on and sit at the computer. The liberty to allow people to do that comes from these two tools.
Okay. Awesome.
All right, this is just a little, whatever. Our philosophy is that, we're working at multi-scale. We work subjectively and objectively. We want to iterate through. We believe that working in this nonlinear way makes things more affordable and faster to the table by building tools that support the design concepts, and I'll show you later how we can make real-time adjustments very late in the game with no loss of, with no increase in cost. In fact, sometimes you'll drop money right at the last minute, so I can show you that. We, for example, as the bridge is shown with its 3 legs, we had during the slab, while they were casting the slab, they hit something that, a root of a tree that they wanted to preserve. So we ended up just opting out of one of the legs and readjusted the shell very late in the game. And, it was no big deal. So it's okay. So these are some of the early models. Is this the second or first slide?
The first one, yeah.
Yeah, so you can see in here some physical models at 1 inch and some bigger shell models. We are drawing on top of the 2 models on the bottom are made of fiberglass, and they became these additive layers that we would cut away and then add some more to, and we draw on them, shoot pictures, and then paint them over and then redraw on them as part of, parsing the shell into different structural systems. The lower right.
Yeah, can you talk about that one? Yeah, this one's interesting.
Yeah, so we did some PVC bents that we used as a full-scale, real-time adjustable tool that the client could walk through. We could talk about because we had this in-place plane that he could walk across, we could relate the new plan to this thing by saying, oh, this should be broader at this point, or we're going to move this vertex this way. And also talking about the ceiling proportionally, relative to the passage, and the idea of having 1 or 2 people pass at the same time, or do you want to have more or less sculptural opportunities in there? So that was the purpose of that.
Okay.
And next one is a version of the acrylic model that we were looking at, some Photoshop work in the lower right, and some Maya in the middle with just different shell types, that we were looking at. And an early version lower is of the voxel logic with a dynamically relaxed surface that the boys at front did for us.
This guy right here?
Yes. So that comes up. We can show you in a bit about that.
Okay.
So next one. This one represents after our earlier efforts. We had a bunch of contenders, let's call them, shell shapes. And you can also see in this image the grid is representing the original surface. We developed physical models for the original design surface. And then in order to make the shell work as a structural shell, we had front do a dynamic relaxation of a surface to approximate our shell shape. And then, as you see in here, we both compromised. They gave a little, we gave a little, and we ended up with something that was a viable shell shape for self-supporting shell.
So this is a bunch of different models overlaid on top of each other. I'm going to say back what you said to make sure I understand it. So you had, let's say, from these studies, you developed a surface that was sort of your target, and then you worked with that structural engineer, Front Design, right, or Front Inc.
Yep.
Front Inc. in New York. You worked with them to sort of apply, structural logic to that, and then you guys sort of went back and forth. They sent you a model. You kind of compared it to what you had. You made some adjustments, sent the surface back to them, and you guys kind of went back and forth. Is that kind of right?
Yes, exactly. And this model is, a screen capture of Rhino. Just me looking at the different surfaces. I'm putting some planes in there to cut it up and to kind of analyze it proportionally, and yeah. So then the next version, if you click, that embodies our, some of those efforts, early efforts, and the very specific choices into the profile, the heights of each of those curves, and the wing as it comes out the backside. Each had very significant, jobs to do in the property. So.
Let me just go back one sec here. You made mention of dynamic relaxation, and that was something that the folks at Form Inc. worked with you guys on. Can you talk about what that is and sort of the process that your team went through to do that?
Like Friado or like the Gaudi hanging chain models in Sagrada Familia, the catenary that's formed from suspending a surface or a line is going to give you that optimal structural shape. So what Front did was approximate some holding points, and you can see it had to be faked a little bit to get it to take off from the right point in our specific site, but they simulated enough of the point of departure where we wanted our shell to start so that they could let a surface dynamically relax in their structural analysis software, and then offered us back versions of that relaxation. And so we'd change a few parameters with them, they'd come back with a surface, and then ultimately we ended up saying, if we make some what would you call it, concessions with our pristine perfect geometry, we could match better the true structural nature of the shell, right? And so, and the one piece down lower, right where you just drew the intersection there, that wing has always been, it had to be considered as a clip-on tie, as I would call it. It's not a part of the structural shape, and so there are moments where trying to decouple the two buildings that we had to make some accommodations, and you can actually see them in the later views of the model where there is a structural frame that rides on the snoot down there. So.
I see. So to say this back to you, so you sort of had a connection point over here along the building. You had these three structural connections where the feet touch the ground, and then you had this connection point here along the building, and as you said, this surface here was sort of independent. And so essentially the dynamic relaxation was putting a surface that was connected to those points and almost turning it upside down, like you said, and use those classic examples, I guess. And then that kind of developed some geometry, but then it probably also developed, some idea about the depth of the structure at these various points and so forth. Is that fair?
We had just the specific locations on the property would have given us some limits to the thicknesses of things. Say there's a window above, on the floor above, so the thickness of the shell at the house had a limit. But there was more specific, as far as the shell shape was, we called that our top of structural voxel, so TSV is what we were labeling it, and that everything worked down from there. So the height of that was just related to leg choice at that point. And early models with the structural draping, they didn't have, you'll see images of them, they didn't even necessarily incorporate the legs at their fullest length. So,
okay.
Yeah.
Okay,
but
cool.
Then, so then we came up with what we're calling a design surface, and it's a relative term because it's not sacred in the sense that it's going to take hits through time, and so next slide you go to, so this is a simple surface, then you have a simple mesh, triangulated mesh. Oh, you can go back one if you would, please. So this is just a simple triangulated mesh of the surface that we developed. Now, if you go to the next one, what we did was we used a plug-in Weaverbird for Grasshopper, which is a Rhino, parametric engine, and we use the Weaverbird script to dynamically remesh. So the red lines represent kind of a sense of weightedness to the mesh, and we were running versions of this, so we'll have many different influences at different times. But initially, we had some very specific ones that we're going after. Later, there became secondary influence of the airflow in the ducts that we were going to use. So, but you'll see as you go to the next one.
Actually, let me ask you here. So these lines that you've created here, did you really use these lines in order in Weaverbird in order to influence the density of the remeshing?
Yep. 3 slides down, I think we'll come to the actual diagram.
Got it.
Here is so the remeshed you see in the first slide to the left, and you'll see the weightedness in the triangles in the background. It's a darkening. And then what happens is we take that mesh, adjusted state, and use a circle packing script, one that was based on a Daniel Piker, who's a coder that uses Python and Grasshopper. And so using that script, we we're able to use the circle packing component of that script to determine relationships on that surface related to that adjusted mesh. And then what you'll see if you look back and forth between, and it is a dual nature of a build here, it's 2 things going on at the same time, but you see the center of the circle, which is in the middle image highlighted in red. And then when you go across to the next image over, you'll see this polygon that's set out from that circle, and the number of sides as each of those sides relate. Each polygon has a range of. We had a few 4-sided polygons, but only as resultants, not as intended. We started with a 5, and we set like a max 10 number of sides as our range. When we were doing our polygons, that's one of the input variables that you can put into the Grasshopper engine that we custom built using the Daniel Piker script. So if you look to the next slide.
Which, by the way, where can you get that Daniel Piker script? Can you get it on the Grasshopper form or something?
Online, you can go on and you can Google and find some different, he has his own website, but I'm sure there are several forums. You can go on Grasshopper forums.
Yep.
So here you see the plan view of the shell, and you see some of these lines of influence that went into the remeshing, and then you see the remeshed mesh in the middle, and then the resultant polygon set for this particular version. We ran this script hundreds of times, 300 probably to 400 times, where we had generated versions, and this one looks close to the ones that'll be on the subsequent slide. So these are probably around 1,000 polygons, but we kept adjusting those variables so that we had sets running down around 400, 450, 500 in order to try and play games between the variables that we were investigating at that time. Gauge of metal, type of metal, whether it's aluminum or stainless or mild steel. And each one of those ends up with repercussions downstream to secondary systems. Say we pick mild steel, then you've got to deal with condensation, in the shell. So, okay, well, let's look at aluminum. And these things kind of feed back on themselves, back and forth. So you'll see in the later images how we investigated that at full scale. So you can go to the next one.
Okay.
So then, you have the extruded voxels on the left, which is just taking those polygons, and in the early versions, as I said, we just pushed them down to a secondary surface that was an offset surface, and they weren't rationalized, let's say. Then we were able to get some structural analysis, though, and use that feedback to play into the. So we use this diagram because the middle one you can see, looking at it as in, I'm not sure which analysis software this is, but you can see the viewing the overall bridge as a beam, that there's a reaction in the middle there, and we just thickened up in there as just a kind of reference for that, not necessarily getting full benefit of the density there, but So you could go to the next slide.
Actually, let me pause here for just 1 second as a side note. Don is asking a question, going back to the dynamic relaxation. Do you know if Form Inc. used Kangaroo to do that dynamic relaxation, or were they using some other structural analysis software?
I believe they used a different engine. In fact, I would say almost 100% that they did not use Kangaroo. We used
Okay.
Kangaroo on this project, but I don't think that was their tool that generated this. And that left image in these two sets are the output from front. Those are the dynamically relaxed surfaces. But I can ask Keon if somebody wants to hit me with email. I'll get them connected.
Cool.
But I don't think it
Okay.
was.
Sorry.
Okay. You could go to the next one. So we had to define, as I said, it's a nonlinear process. So early voxels here were built as we were still exploring, structural types. And so the cardboard ones and the plastic or, polygal ones there, those were done a long time earlier in the process before we ever got our script rolling and things like that. We were trying to investigate ways of making that structural shape off-site with a high degree of control and a high degree of flexibility. So we knew, I'll show you in the next slide actually. These are early examples. You can go to the next slide.
Okay.
This gets into the rationalization of the voxels. So on the left, you see the doubly curved surface that represents the outside TSV, topostructural voxel surface, our design surface. So it's doubly curved and therefore, there's no faceting. But with the voxel world, we had to rationalize the geometry, to accommodate the planar nature of the tops. And you'll see that you have this little slippage in the lower right image where there's faceting. And so that just made us address those secondary systems, the tile system, differently, because we couldn't use this as our outside shell and express that. So you can go to the next one. So this is that rationalization moment, taking the polygon top and bottom surface. The bottom surface was not generated as a straight numerical offset. It was developed as a set of investigations underneath, and we wanted to have a change in topography, a thickening. As the shell moved out towards the edges, it got thinner, and different parts it was thicker to carry the airflow, and then, so there's different things driving the Z depth of our space between top side of voxel and bottom side of voxel. So it looks somewhat straight-sided here, but it was not. And our output, our model had an output, in an analysis format that we could look at and see, the average sidewall dimension and the aggregate sidewall dimension. And so, anyhow, you can go to the next one. So to get the faces to align from one to the other, from that simple geometry outlay, the beginning polygon, you have to average sidewalls. And so Vish wrote this script that cleaned out the corners so that there was a little bit of room on the intersection to give a little tolerance, and then he averaged the sidewalls, trimmed out these nodes, and then if you go to the next one, he's come back with a sidewall that represents the the resultant of this little script. And in the end, you can go to the next one. Let's see. So actually, one more I think is the full.
Well, actually, maybe just as a side note, I think this is where you're starting to show. You referred to this a couple times, but I think maybe this is one of the first moments where you show. You've talked about this as sort of this structural system, but here you're actually you're creating some holes in that system, and so. What's interesting about that is, remind me again, how are you using these holes, or at this stage of the game, what is your intent on what they're for? And actually, you even have the ones at the bottom surface here, where maybe something different happens down here. Can you talk through that?
Yes. So the side holes were knocked out for two things. Three actually. We started saying, let's have some ability to pull systems through, whether it was a high velocity air system or whether it was electrical or whether, some plumbing, and we wanted to, lighting systems, things like that. We wanted to accommodate them, so we always had this notion of some knockouts. But then with the thickness of the shell being adequate enough, deep enough, we thought about using the shell itself, because essentially it's just a sheet metal box like a duct. So we went to our mechanical engineer and said, give us our averages of duct size left and right, and we'll be highly inefficient in our duct, because these openings are so much smaller than the panel that they're sitting in. So there's a loss of efficiency, and we got to worry about noise and things like this. So we would go with a low pressure, and just let the air eat through these holes. And then, of course, we're introducing changes to the internal temperature, so we've got to start thinking about the insulation system in relation to that, and back to our primary material, are we using aluminum, which may oxidize, are we going to use stainless, and what are the weight differences? And all of these are kind of pumping back and forth at the same time. We always had a knockout on the bottom simply because workability, and we always thought that these things would be riveted together at least into aggregates like you see in this particular image, maybe 5 to 7 minimum, right, in the shop, and then brought out to the site and then banged together there. And then you see in the next slide that we had shards, as we were calling them, much bigger chunks. Actually, one more down goes to there. So the different colored, sides of the bridge image. Yes, exactly. Those guys represent where we were considering assembling these, trucking them out. That's all based on the truck width and the road, and we have a lot of issues on the road up in this site. So we had gone through it in the previous project with the jumbo glass, which was 22 feet crates, So we had a sense of what we could get up into the site and pick into location. So they were going to be riveted. You can go back to the one with the holes in it if you would. Yeah. So they're going to be riveted together, even if it was just to hold them as a staging, get them into place, and then tack weld as your kind of added extra strength. And we, in the latter structural design, ended up conceding that we had to do at least the top side layer, tack welded each 2 per edge, So we're going to have these things come out riveted together, and then once it's fully formed on site and ratcheted down into shape, it's going to have tack welding on the outside. So.
Okay, so you're using these holes for access down here, maybe lights sometime in the future. You weren't sure. And then certainly for HVAC and so forth.
Sidewalls for systems and bottom for assembly, basically. And then because you have the hole in the bottom, then you can use that for secondary systems of light or air. So.
Yeah. Okay.
So this just goes into some of the versions of tabbing, because there's a whole bunch of relationships of offsetting tabs so they don't hit each other, and labeling. And one of the things that we are aiming to do, which I mentioned in passing earlier, is flatten out the fabrication process, maybe simultaneously fab sets of these in shops locally simultaneously. And one of the things we're after in our practice, as we want to lower the bar on the labor side by using our information to the max, right? So if we're labeling these in a certain way and studying them in a certain way, that it's a natural process that someone's going to go through to assemble these. If you go to the next couple of slides, there's a let's hold there, I guess, but I'll show you when we have the pictures of how we folded in our shop to test for.
And John, let me interrupt for a moment, because there's a point there I want to make sure that everyone's catching here, which is you're actually talking about crowdsourcing the fabrication of these voxels, and sort of this idea that if you develop a simple and clear system that you're going to get into right now, that anybody, as you said a couple of days ago, anybody could take one of these things in their shop and fabricate one of them, so that it didn't necessarily require one shop to fab everything, but you could do it in multiple shops all over, the region that you're in, or something like that.
Yeah, Yeah, the perfect little sidebar story to that is we made for the gallery, we had a 3,000 square foot doubly curved stainless steel,
And the gallery is a different project that you did prior to this, right?
but it had 30,000 connections, doubly curved surface. The spacing was like 4 to 5 inches on this web net. And we ended up getting that made for $3,000, 10 cents a crimp, because we gave them one-to-one rolled out templates of, connect this dot to that dot, and then parsed it back into one bigger shell, So anyhow, it's something that we do all the time as far as our practice. And the next image, the one we're on now, you see the unrolling and the packing of the sheets as well. So we're talking about sheet size and who's going to be the, person doing the laser cutting early as well. So we're working back and forth. And then on the right of the top set of image, part of that image, you'll see some of the feedback that's from the Grasshopper model. So we're getting resultants of, different, if you zoom in on some of that, you'll see, thanks. Yeah, sidewalls, top, total weight, and length of line, sometimes relating the length of line of cut to the laser cut rate, and yeah, so just some of the feedbacks that we get for every time we do a run. All right, you could go. All right, thanks. So these are versions more of the voxel using that circle packing, the script. Then you can see some different versions. These are all relatively similar counts, but just a pretty obvious expression of the difference of each one of them. And those are actual product. These aren't made up, for anything. These were out of our set. So.
And this is when you're iterating on trying to figure out how to which materials you want to work with. You're trying to figure out, how to get the number of voxels, the number of unique voxels down, so that you have some, let's say, standardization or something like that. That's what you're representing here with these 10 variations. Is that right? Is that fair?
Yeah. If you look at the next image, the resultant that we ended up picking, basically, what you see is you're going to see the polygon geometry carry through all the way through to the tile. So arrangement, layout of these sets is going to impact the, what we call the object state, the way this thing sits as a building in the landscape. You're going to see the patternization of these voxels. So these early studies weren't just looking top down. You're looking at them in perspective, in the model itself, and moving around and taking a look at the way that these play with each other as you move through the site. We want them to have, so say, take the middle one, top side, that's so, brindle looking or striped. That may play very differently in situ, as opposed to how it looks right now planned down, right? So it looks like it's just some wacky little stripy guy, but really when you get into the three-dimensional domain, you start to see this play against the, the thickening of the sets,
Okay.
All right. So this is our, evolution. It takes time, or it takes a high count. We tend to use a high count. We use digital tools to generate high counts, and we're looking at multiple scales, multiple states of reality, as we call it, multiple relational networks, in terms of how I was speaking about how a choice of, what the voxel is going to do is going to change your material type. All of these are cross-graining. There's many variables impacting simultaneously in a nonlinear fashion the other sets of variables, the relationships, of decisions. So
I thought one thing you said that was really cool about this, or maybe the way I maybe understood it, is you talked about how digital tools give you opportunities to create context, because the iterations, so all the digital iterations that we do, those iterations become the context. So once you know that I already created this and I don't want this, I want that, so those iterations become the context. Am I understanding that right?
yeah, in what we call it, probabilistic solution set. By the time you're here in the game, there's so much information generated that we're looking at it, you're correct. You're seeing it in a context. And that's why I use that analogy of the snake eating its tail as far as our, design philosophy, because you need this motion to happen, you need this set to emerge, and you need all this information to be out there so that you can actually refine those sets. And the context is, in setting, once you decide, like if you go to the next image, actually, I think that's the beginning of, we came to a set, let's call it. It wasn't the final set, but it was a set that we said, okay, this is basically the number we're going to use, the general arrangement of how they're going to be set out on the shell, and how they'll work, in terms of thickening. And we've run this into the rationalization into the voxel set. So we've looked at this guy enough to say we can move forward with this particular version as 90%, let's say, solutions at that time. But you couldn't have gotten there without having all of those other iterations. So okay,
Makes sense.
so next question. Okay, so here we were using the shop to generate feedback, testing the rivets, testing, again, the holes. We did, each one of these may have been from a different material because we wanted to see the way that they would bend, and the way that the stitching would. We've done different versions in which there are, a stitched seam cutting out every other, so that it folds better and cleaner to an edge. We did versions in which the top was attached to the sheet, looked at the efficiencies of, optimization of the sheet that way. So you can go to the next one. These are just images from the shop, looking at, folding in tabs and some labeling, perhaps, just to get feedback from. So you can actually see in the background some flat stock there as well. So we had 2 or 3 different laser cutters, and we would be shopping around for a price to do the big job, and so we would use our conversation with them up front to get some samples back. And pardon me. So we would be saying, we're looking at doing this much square feet. Can you give us a couple of, stainless or some aluminum? And so you can go to the next slide. You can see how the voxels, they fold together. The tabs get out of the way from each other. There's labels on the voxels themselves that, help coordinate the set as it goes out into the room or into the site. Yeah, could be. Yep, could be. Yeah. And then the rivets, the holes aligned, they're all cut in the stock sheets. So we're not post-drilling. You can see the burnout on the hole there. And the bottom on the right side has, does the work of binding the 2 tabs together. And so you can go to the next one. And there you see a set, that we put together in the studio, again, to have that full-scale relationship with, the secondary systems you'll see in a second as well. So we use this rig, which we generated as part of that problem setting, to have conversations with our structural engineer, have conversations with our fabricators, have conversations with the client, and all the other secondary engineers. So this is the voxel layer. You can go to the next one. So once we had that set of voxels moving, we started looking at the top surface and the bottom surface. Bottom surface for us was what we were calling the visual voxels, right? And because we had come up with a bunch of feedback on how the shell should behave structurally and how it would work dimensionally and the set itself, we looked at this secondary layer as solving some of the inadequacies, let's call it, of the shell, right? So there's a visual appeal to this layer. There's also some sound attenuation. There's some texture and some color that we're getting into there. We're also looking at it as a secondary insulation layer. And another thing that we believe in is that though the relationship is one-to-one, polygons that are in the structural voxel layer are tied to the visual voxel layer, you'll see in subsequent slides that we could change our material set and radically change the underside character of this. So it wants to be a swappable system. Essentially, if 5 years from now, Arthur, the client, wants to change it out, he could hire someone to make another version of this. And that's part of our whole principles for this particular property is change and intentional change. So you can go to the next
just to
slide.
be clear, just want to make sure everyone's following, because this is a super interesting diagram. So this This is the sort of obviously the upper layer that you're talking about. This is that visual voxel layer, right? And then this space in between here, this is the structural voxel that we just looked at here, right? So there's this.
Next image is another. There
you go.
So you can see the little system of tiles that goes on the outside. The concept of using a standoff there, which is tied back to the geometry, and waterproofing layer, and then the voxels, and then the visual voxel, as you just pointed out.
Yep. Makes
All right.
sense.
So this section is just for reference, with the glass and a long section through there showing the basic topography of the inside of these visual voxels. So you can go to the next slide. So these were early versions of, digital renderings that showed some texture down there and some sense of how the visual voxels wanted to manifest themselves. And then you see we did some carved on. We have a 5x10 CNC mill, and we used it to carve the foam on the upper right. We made our own versions of corrugated, playing with concepts of color and texture. We did not hundreds, but probably 50 or 60 versions of these physical models that were kind of looking at the textural aspects of the visual voxels, independent from the digital realm. So we're looking at the performative or the phenomenological characteristics of the ceiling surface and fishing for a set of attributes that we want to explore or exploit in the digital model. So you can go to the next slide. These are my alliteration moment. But you can see in here there's multiple different types of visual voxels. And in the later image, you'll see the digital rig that we use to generate the carved most left two sets. So the one with the red and then the one higher up, which is smaller scale. Those guys were carved on our mill. And the point is that the digital tools that we want to build have an extensibility, let's call it, into, so we can change the order of the spline, and go from a smooth, higher version, is a smooth surface, no vertices whatsoever, to a very faceted and kind of almost uglified in the lower one with the red. We were messing around with like noise and on these surfaces where we were getting, sharper edges emerging, and you'll see different versions of that to the right as you go across, but some of them are carved, some were cast, some were heat formed over jigs, some are fabric, some are cardboard. But all is a way of trying to get some texture, color, and topography into the underside of the bridge. So you can go to the next one. Is just a interim study of looking at minimally invasive again. So how could you do it in the cheap and cheerful version? Would be with a fabric that pulled back to a single point on the upper side of the structural voxel, and using some LED pucks and things like that. We are looking at creating a skin fabric on frame, and that would be very easy for us to do in-house if we wanted to. The next image, which you see, is a version of one which would be done in milled foam, some built-up aggregate milled foam pieces. But so some were very deep, some were smaller and flat. And you can go to the next slide. This talks about the rig which we built, which is, when you're looking at this diagram, you see these two lines at the bottom called interior datum and exterior datum. They represent surfaces that we generated underside of the bridge, offsetting originally the bottom of structural voxel, BSV, and then manipulating that surface. And so there's two surfaces, and pardon me, in subsequent slides you'll see those surfaces. Actually, you want to go to the next slide? And that shows the surfaces. So each one of those represents versions in which the interior and the exterior datum play a game with each other, right? And can you go back up one more slide? Mm-hmm. What that does, no, actually, so to slide, what is it, 46?
Yep,
there we go. So in this, the red and blue lines, you see them in the axonometric or perspective view up there. But those represent vertices, which I could change the order of and have it not be a sharp intersection, but it could be a softened edge. And by reversing the relationship inside to outside, you can get, literally innies or outies, where the ones in the back are kind of protruding past the blue ring, which is the outside line that they're on. The reds in the back are all positive, and the ones on the lower side, you have these innies, where the inside surface is dominating. And then we have control over the aperture of all of those in relation to each other, by controlling that with the little slider, right? So there's the blue surfaces, aperture has a game with the, and in some there'd be a huge hole and just a little bit of massing. In others, you see a ton of massing and a tiny little hole, and that was definable. And so our versions were games of playing with the two surfaces in topography and the Z and the shape, and then playing with influence curves to change those apertures in relation to each other. And I was saying to Mark earlier that in order to see these correctly, we had to render them out and do video walkthroughs, so that you could actually review them later. So one of the guys, Sam, would make a set of videos. We made hundreds of these videos, and it was very memory intensive. But to be able to review them, you had to see them in situ, and so the walkthroughs were, it was just a very useful tool that we built.
So let me ask you a question. So you're referring to this visual voxel rig. So sort of in layman's terms, it's a Grasshopper definition that you've built, correct?
Yes.
And it has, as you're saying, you have various parametric controls that control, as you said, the Z direction for the red lines and the Z direction for the blue lines, as well as the aperture, which I think you're representing here with this sort of dashed black line in the middle. I guess, so, and then you mentioned that you're using influencers, almost like the classic Grasshopper kind of tutorial where you have the point and everything close to the point has a certain bigger radius, and everything further away has a smaller radius. So I get that part. What were you using? Were you using similar points sort of in their Z location maybe to influence the Z direction of the red and the blue lines?
No, there would be a set of law curves that were, splines that were generated they were longer axes tools. We had sets of lines in the.
So it's maybe something like the greater that as maybe that those lines, as they moved in sort of in space, the higher they were, the greater their Z value, then that was influencing the red and the blue lines. Is that right?
Yeah. So it's a little tea leaf moment as well, that you can have a 3-axis relationship with the attractor, and it's going to be up to the operator to generate the vibe. And so if you go to the next set of images, which are the next one after, which is the versions, you can start to see. Again, you're making the set to get the feedback to say, okay, well, I'm going to fine-tune it a different direction here, or I'm going to change my incremental assumptions down to X or Y, And so each one of these we ran, because they were so operator-intensive, we ran versions which were a set of curves were adjusted, a geometry was created, and then a set of secondary variables were adjusted, like for the apertures. And so we could use that same move in multiple different ways. And so when you look at these, there's a general geometry that's going on in here, and then the secondary geometry influences the primary geometry, but basically they're all the same primary geometric move that you're seeing in this upper left is propagating out, and it's just depending on whether you're opening up or closing the cells. And so we would go through the exercise, painful as it might be, of adjusting it minorly and doing it as a faceted piece, and then making secondary adjustments, doing it as a faceted piece, and then coming back and doing it as a smoothed out set as well. So It's extremely labor intensive, but that's, the point where the operator starts to really vibe the piece, then you start to get some production out of it, and things go fast by the end. So if you go to the next image, I think there's another set of views, in which we present these in, 2 or 3 or 4 sets at a time, have a conversation about it, make some minor adjustments, and go back at it. So, and that's the rig again. It's the black and white version, and these are some high density foam pieces that we milled on the mill, and this particular one starts to talk about the introduction of color and that gap that was driven between the side walls of the starting to shape that area and allow that to bring in a whole different scale of pattern and color into the underside. So, and that's built onto the piece that we had just built previously. So then, now this one is the tile. We can go through this quickly. I think we're up close to the time. But this is another zoomed in sectional view. So looking at the tile system. Yeah, go ahead. You can go to the next one. So this is, you want to show your little...
Yeah.
Okay. So this is a tool that we built using the original voxel packing, and as a video, you could run this and then take screen captures, freeze it, and take screen captures, and then do studies, color, change the color layers, change the fills, and do some analysis to try and generate some patterns that would be on top of the tile system itself. So we were going to take these triangulated tiles and incise on it a pattern that tied out over the whole top of the skin. So.
Awesome.
And this was a little dynamic tool that was very helpful.
And it's a tool you built in Grasshopper?
Yeah, and then recorded the video, and then, but what's nice about it is that you can send this on, and it's reusable for some other things as well. But it's a high degree of utility.
Yeah.
So, yeah, and then this goes into how we were looking at the original geometry, the polygons, which are the first start out point, and then how the tile system started to relate to that. This image here shows a much better, you can see in red the original polygon of the packing that we did originally.
So the structural voxel there, basically, right?
Yeah, exactly. And how it shares its edges are actually fold lines in a multiple 6 shared triangular tiles, and each tile was related to the original base geometry. So if you go to the next slide, you can see the way that manifests itself. So we did a little full-scale mock-up and trying to do a simple bend in a triangular tile and generate this whole cladding system. So the next slide, these are some versions using the little design tool. And yeah, that's coming back to the end of line.
Awesome. There were a couple. Let's talk through this, because this is really interesting.
Yeah. So this is an overall diagram of the process, starting with our design surface, and it shows circle packing, and then the mesh remeshing, surface panelization into the and the voxelization from that. We can go to the next slide. Voxelization splits into, on our right side is some of the secondary systems that we had to do, the glazing package, and some of the rationalization of the attributes of the voxels. On the left, we had the panelization. Let's see, what else? Bolt location. There's a whole bunch of structural analysis that went into both strands down that side. I'm going to, I don't know if you want me to send you a link, Mark, to one of the structural papers. I think that there's some interesting stuff in there that I didn't want to get into, but...
yeah, we can share it with everybody for sure.
Yeah, okay. I'll send it to you and you can make it available if you want. So,
Cool.
all right.
And then let's see. Yeah, I think we should conclude on that one.
Yeah, okay. So this is just back early image when they had, a dynamically relaxed surface with the polygons packed out on it. And we were just mashing it up over the top of slab and glazing to kind of seek out a shell shape early. So,
And it's quite beautiful, I have to say. Okay, so let's see here. So we do have one question. We've had a couple that we've kind of sprinkled in along the way. If anybody has any other questions they want to share in the with us, please do so in the GoToWebinar question box. But I'm going to start with Joshua here. He said, and I think this was back when we were talking about the mind mapping software, and we were also kind of overlaying that with working with other groups. And he said, at what point did you start consulting with, and how easily were you able to interface with the structural and mechanical engineers? That's a topic that you and I talked about as being a really key part to the realization here. So can you talk through that and your advice, I guess?
right. We had a working relationship with Front since I think 2003. I saw Marc at the Smart Geometry in Ontario, and they had 4 people in their firm at that time. We've always seen the world very similarly. I think those guys are great problem solvers, and I think that we end up, starting on the problem setting side more and using our tools as investigative and design generating versus, so because that relationship existed, our initial relationship with the gallery when they did that set for us, we started in a very loose, trusting relationship, before they had any of the integrated project delivery contracts out there. But it was, a known thing that we had to work together to generate enough information to be sure that we had a viable thing that we were going to be able to go forward with. So having had that experience with those guys on the structural side very, very early on, before we even had our own resources rolling strongly, I had called Marc and said, can we get you guys to take a look at this and think about how we're going to approach this shell? And so he gave us 2 resources dedicated, X% of their time to our project, and even before we knew what we were going to do. And that helped actually drive, the set of decisions, because the capacity that they brought, it helped influence the whole project. So, and on the mechanical side, it's not that we don't pull in the mechanical early. It's that, I think we had a real strong sense of the nature of it. And I wanted this thing to be that integrated design where the shell itself was its own, breathing element, its own conduit, its own everything. And so because we had that at the outset in the back of our mind, it was only when we started getting into actual volumes and concern about, the behavior of the air and stuff that we got our engineers involved. But we had kind of had that lurking for a long time in the back of our mind. So, yeah.
Awesome. All right, well, I'm going to end it there. So first of all, thank you, John, so much for sharing this amazing project with us here at our inaugural Super Simple podcast. And thanks to everyone who tuned in and who submitted questions today. I'm excited about this idea, this podcast idea, and I'm excited to hear any feedback, any other ideas you guys might have for future episodes and things you'd like to see. As I mentioned at the beginning of our session today, if you want to attend our next Super Simple broadcast on June 8th, where we'll feature Andrew Watkins of Ira St. Grove, where he's going to talk about using digital coordination through the design and construction process on their AIA TAP award-winning project for the University of Delaware's Interdisciplinary Science and Engineering Lab project. Make sure you go to blackspectacles.com/podcast to register for that episode. And to learn more about the software tutorial curriculum I mentioned earlier, go to blackspectacles.com, where you can watch any and try out any of the free course videos. And for those of you who are ready to start learning some new design tools, you can use coupon code 51116 SS15YT to get a 15% discount for the entire duration of your Black Spectacles software tutorial membership. And then finally, please leave a comment below the video here so you can let us know what you think. Share any suggestions that you may have for additional content or other ideas you may have, as well as ways we may do this differently. As we always do, I promise we'll read every word that you write and use them to tune our next episodes. So thanks for watching.